Okay, so let's get started. Last lecture we were looking at operation of MOSFETs, and this was the last slide in the last lecture here. And we were looking at that we can of course make two NMOSes side by side on the same silicon wafer. We can make two PMOSes side by side. We can make, of course, NMOS next to a PMOS as well. And one of the things that you notice from this particular figure is that, as I said, normally the substrate is p-type, and therefore you can directly make the NMOS transistor on that p-type substrate here, because the n-type MOSFET requires a p-type body here, and n plus source and n plus drain, and therefore you can directly, on the p-type, you can create a region n plus here and an n plus here, and then deposit oxide and make the transistor. And similarly, you can make a transistor here. What you notice from this particular diagram is that all the NMOS transistors, they share a common body. The body terminal, the body is the same for all the NMOS transistors. And typically what we do is we keep the body at the most negative potential in your circuit. If your circuit is, let's say, running between +3 and -3, what you would do is you would put body at -3. If the circuit is running from 0 to 5, you'll put the body at 0. The most negative point is connected to the body here. And the reason is, when you make this body p-type as the most negative point in your circuit, what you're doing is you're ensuring that the source body junction never gets forward biased. The source body junction will always be either reverse biased or at the most zero biased here. Which means that there would be no current flowing between the source and the body terminal here. And drain, of course, is at a higher potential compared to source, so that if you ensure that source body junction is reverse biased, then drain body junction is also reverse biased here. So it ensures that source body, drain body, all these source body here, drain body here, all these junctions are reverse biased. So note that even though these two transistors share the same common body here, if I look at drain here and I look at source here, between the drain and the source, I have, between n plus p, I have a p-n junction, which is reverse biased. And between this and this, I have another p-n junction, which is also reverse biased. So any two terminals that you see here will be connected through two reverse biased p-n junctions. And therefore, no current really flows. So even though you've made the same transistor on these two transistors on the same body, the two transistors are isolated from each other. They do not interfere. Whatever I apply here, the voltage here will not influence the current that flows in this particular MOSFET here. Okay, so the point is, the body is kept at the most negative point in your circuit. PMOS, on the other hand, you can see here each PMOS requires an n-type body. So what we do is we take a p-type semiconductor and we convert a part of it. This we call as an n-well, and we make a well here, and within the well now we make a p plus and source and drain, and we make the p-type MOSFET here. And each p-type MOSFET, you can see, has its own separate body terminal here and a separate body terminal here. And therefore, the body of the two PMOSes that you see here can be at different potential, unlike the NMOSes. Of course, I have a choice also that I can make two PMOSes in the same body as well. I can make a larger well here. For example, I could have made one single well, and within that well, I could have made two PMOS transistors as well. That possibility is also there. And but anyway, p-type MOSFETs provide you with the option of a separate body voltage that can be applied to each transistor here. Okay. Yes. Dimension. So this is a rather simplified schematic of the bipolar. Of the MOS transistor here. This is a more accurate picture. You can see here more accurate picture of the MOS transistor. So this is your gate here is polysilicon. This is your oxide, and there's a thin oxide here. Polysilicon is heavily doped and it acts like a conductor. So that's the gate. And in between the gate and the semiconductor here, you can see there's a very thin oxide here. And you can see also the dimensions here. The dimensions that you're asking for are also given here. If you look at the whole thing is For example, this particular MOSFET is about 0.5 micron channel length here. Starts from somewhere here to here is the channel length. It's about 0.5 micron. And these regions are, you can see here by these lines here, these regions are actually, it's not shown, but these are N plus. This whole region is N plus. This whole region within this boundary here is N plus here. And this, of course, is P-type. And you can see the depth here, maybe, 0.15 micron or so, the depth here. And of course, the whole substrate, one has only shown a part of the substrate here. The substrate itself is about 300, 400 micron thick. Okay. But as I said, all the action, of course, takes place right at the surface. Okay. So these are, and this is, of course, source terminal here and a drain terminal here. So that's a more, here we had shown all very sharp edges and all that. You don't get that. That's a geometrical drawing. Actual boundaries and all that are always more gradual, and so that's a more realistic picture. But again, this is also it's not a real cross-section of a real MOSFET. It's also a more realistic MOSFET that's used for simulation. All right, so let's come back. So we have seen the structure, we have seen N-type and P-type MOSFETs. Let's look into the operation in a little bit more detail. So what we have now is an N-channel MOSFET. So we have N plus source and drain, P-type here. And I mentioned that one of the voltages or the parameters which is important is the threshold voltage. The threshold voltage marks the point where I begin to get a strong inversion. A strong inversion begins to occur in my channel here. Okay. So we take it as a boundary. Although the moment you apply a positive charge, you start creating more and more electrons in the channel here. The channel becomes really strong once you cross the threshold voltage here. So we, for discussion, we'll take threshold voltage equal to 1 volt. Okay. And threshold voltage is equal to 1 volt. So we have source which is grounded, drain grounded, body is also grounded, and I've applied 2 volts to my gate here. Now when I apply 2 volts to the gate, the voltage 2 volts is larger than threshold voltage. It means that there is a channel which is there at the interface between the silicon and oxide. So that's the channel, the dotted line shows you the channel. Now the issue is how much charge do I have in the channel? Since the channel is made up of electrons, we call it an inversion layer. So the issue is, what is the magnitude of inversion layer here? How much charge do I have? And that we can see that the charge will be equal to, it's a capacitor. You know that there's a metal, there's an oxide which is an insulator, and the sheet of electrons that you see here, it acts as the other plate of the capacitor. So it's like a parallel plate capacitor. And in a parallel plate capacitor, you know that capacitance per unit area is E by T oxide. That's the capacitance per unit area. This is the permittivity of oxide. And this is the thickness of the oxide here. So that's the capacitance per unit area. The charge at any point will be equal to Q inversion. The charge is nothing but Q equal to CV. But note, it's not simply C times V, it's C times VGS minus VTHN. Because it's only when you cross the threshold voltage do you get substantial inversion charge. Okay. Before threshold voltage here, what happens is as you apply a voltage, the voltage is used mostly to deplete the channel, deplete the P-type semiconductor here. So the charge that you create, so anytime, of course, you must be wondering that what happens if I apply 0.5 volt? Well, if you apply 0.5 volt, of course you have a positive charge here and you have a negative charge here. But that negative charge is due to the acceptor atoms here. Because what you've done is you've pushed the holes away from this region here and the holes come and sit over here and you are left with acceptor atoms here, which are negatively charged. So before threshold voltage, what you're doing is as you are applying the voltage here, you are actually depleting the P-type semiconductor more and more, and the charges that you create here are depletion charge. Once you cross the threshold voltage, the gate voltage that you apply here is used to create primarily electrons here. And how many electrons do you get? What is the inversion charge? This is the formula here. Q inversion is C oxide, oxide capacitance, VGS minus VTHN here. So this charge is also charge per unit area. So we are talking about charge at any particular point in the channel is Cox, the effective voltage across this particular capacitor here. So as I said, the entire gate voltage is not used to create inversion charge. The effective voltage is VGS minus VTH. That's the voltage that is used to create the inversion charge. Okay. So we get inversion charge, and how much inversion charge we can calculate using this particular expression. So that's the scenario at zero bias here. When the source is zero, drain is zero, body is zero, and I apply a gate voltage here. The stronger the gate voltage, the more the gate voltage, the larger the inversion charge that I get. Okay, so that's at 0 volts here. Now we apply a voltage to the drain. When we apply voltage to the drain, two things will happen. The first one is, of course, I have an inversion charge. I have a channel which is connecting my source and drain. And the whole thing is like a, I have N plus, I have an N layer here, and I have an N plus. The whole thing is like a resistor. And so when you apply a voltage, what happens is electrons start from the source, enter the channel here all the way, and they get collected at the drain side here. So a current starts flowing because I have a connection between source and drain. That's the first thing that happens, which is obvious. The second thing that happens is when you apply a voltage here, 0.5 volt, note that the voltage in the channel here will be 0.5. As you go further into the channel here from the drain side, the voltage will become 0.4, 0.3, 0.3, 0.2, 0.1, and eventually 0. Okay, because 0.5 is applied here and 0 is applied here. So voltage along the channel is changing. The highest voltage being here and the lowest as you reach the source side. So the voltage in the channel is changing. And what happens is then the inversion charge at each point now becomes different. The inversion charge, remember, at each point was the effective voltage across that particular point. So it was Cox VGS minus VTHN. So that was the earlier, the inversion charge. Now, in addition, earlier we had ground here. Now, when we apply 0.5, in addition, we have a voltage in the channel here. So the effective voltage, which is used to create the inversion charge, is now VGS minus VTHN minus Vx. Vx is at any point, whatever is the voltage in the channel. So what this tells us is now that the inversion charge would be highest close to the source where Vx is 0 and will be minimum close to the drain where Vx is highest. Okay. So now the inversion charge that you see here is no longer uniform. I have more inversion charge here, more channel charge here or inversion charge here, and lesser as you go towards the drain. Okay. The moment you apply a voltage here. So it becomes a non-uniform channel here. So this is the picture that we have now. This is when you apply 0. 0 here, 2 volts. And you can see here is a schematic description here. You have uniform channel here. Channel charge, same here, same everywhere. The moment you apply a voltage here, the channel charge, this charge, remember, is not affected because the voltage here remains 0. Because this is always connected to 0 here. So the voltage, the channel charge remains the same. The channel charge here becomes less. Okay. And becomes less here, and that's depicted by showing that, the channel is narrower here. Okay. At this particular point. So that's what happens when you apply a voltage. The channel becomes non-uniform. Alright. Let's look at how current flows here. Now, as I said, you can think about this channel as simply a resistance. To the first order approximation, you can think of it as a resistance. And if I take a part of a channel, small element of a channel, then this resistance, as all of you know, resistance is rho L by A. So if I take a part of the channel, let's say of element dx, then L is dx, area is width into thickness of the channel here. Okay, so that's the area. Remember, when the current is flowing like this here, the area will be perpendicular to the direction of the current flow here. So perpendicular to the direction of current flow, area would be thickness of the channel, and the width is perpendicular to the plane of this particular figure here. So W into T, that's the area. This is the length of that particular element here, and that's the resistivity. Resistivity of that particular part. Resistivity is 1 by Q times mobility and times the number of electrons in that particular channel here. So that's the resistance here of one particular part. The total resistance will be, all I have to do is integrate this particular part, and I will get the total resistance that is there in the of the whole channel here. All that I'm trying to illustrate through this is that the resistance of the channel obviously depends on how much inversion charge I have in the channel. Okay. And since inversion charge in general, inversion charge is nothing but electrons, since the number of electrons in the channel is varying, and therefore I have I have to do an integral. It's not simply a product of electrons and L. Okay. The current that would flow in my device will be equal to the drain to source voltage, net voltage across this particular channel here, divided by R channel here. And obviously, if I don't apply any voltage here, VDS equal to 0, R channel is finite, and the current is 0. So that's the situation at when I don't apply any drain voltage. When I apply my drain voltage, as I said, the channel has become non-uniform, and because it has become non-uniform, note that the channel resistance is larger than the channel resistance when I don't apply any voltage. Because channel resistance, that's what I'm trying to show you, channel resistance depends on the total amount of inversion charge that I have in the channel here. And the total charge now you can see here has decreased. The total charge has decreased, and therefore my resistance of the channel has gone up. The moment I apply a drain to source voltage here, I have lesser inversion charge here, and the inversion charge gradually builds up and reaches the value that you see over here. So my resistance has gone up because the amount of electrons in my channel is decreased, and resistance has gone up. But I have a current which starts flowing now because I have a drain to source voltage, so VDS by R channel will obviously be greater than 0 because I have a positive VDS here, so current begins to flow. Now you can see that two things are happening. As I increase my drain to source voltage here, the numerator increases, VDS increases, and what happens to R channel? R channel also increases. Because the larger the drain to source voltage that you apply, what would happen is the smaller the inversion charge here becomes, and throughout the channel the inversion charge decreases, except very close to the source where it remains practically constant here. So now what happens is, as you increase VDS, current increases, but R channel also increases. Okay, so two things are happening. So you can see the effect on current. Current increases because you increase VDS, but at the same time, R channel also increases here. So this is the kind of a current voltage characteristics that you get here. This is the drain current, and this is the drain to source voltage here. Okay, so this is the drain to source voltage here, and I'm looking at the current. So what happens is, you can see here, as I increase my drain to source current, my current increases. Obviously, current will keep on increasing. But what happens is, the current starts to depart from this linear line. So initially what happens is, note, if I look at VDS by R channel, so what happens is, initially when the voltage is very small, R channel doesn't change that much. Okay, so current increases linearly. R channel is not changing too much because the effect of VDS on the inversion charge is small. It doesn't change that much, and therefore the current increases here. But as you make VDS larger and larger, the current no longer increases linearly because the change in R channel also becomes significant. So R channel also starts going up, and therefore it starts bending here, denoting the fact that R channel is increasing. So it no longer increases linearly like this, it starts bending there. Okay, because the R channel is also increasing. And as you keep on increasing VDS, R channel keeps on increasing here. Eventually, you reach a stage where you can see that my current has actually become constant. Current has become constant. We'll see why it becomes constant in a minute. But it becomes constant, and it becomes constant at a voltage which we call as VD sat, as a drain to source saturation voltage. Why? Because the current has saturated here, and that's the onset of saturation. And this is the region here where the current has saturated, meaning current is no longer changing with drain to source voltage here. So that region is what we call as saturation. And this region, which is initially linear and then starts bending, so we call this region as a linear region, also called as a triode region for historical reasons here. So linear or triode region here, and saturation region here. Now at this point, it's important to be cautious, because what happened was, in bipolar also was like this here. Current was increasing and then saturating. In bipolar, we call this region as active region, and we call this region as saturation region. Okay? And while here, this is the saturation region in the MOSFET. Okay? Where the current has saturated, we call this as saturation, and we call this as a linear region. Otherwise, the shape sort of looks similar. That current starts and then eventually saturates. In bipolar transistors, this point was around. We used to call it VC sat, saturation voltage, and that was around 0.2 or 0.3. In this case, this voltage VD sat, one can show that VD sat is equal to VGS minus VT. Whatever is the gate voltage that you apply minus the threshold voltage here. And this one can be pretty large. Note that if I have a gate to source voltage which is 2 volt and threshold voltage is 1, so I get 2 minus 1, which is 1 volt here. So the boundary between linear region and saturation region, VD sat, is 1 volt here. It can be 1, it can be 2, it can be smaller as well. It all depends on how much gate to source voltage you apply. Unlike a bipolar transistor, where this point was approximately fixed around 0.2 or 0.3, this was relatively constant. Okay. So saturation region is here, and saturation region for us is the active region. In a MOSFET, the active region is the saturation region here. This is where you would bias your MOSFET in order to make an amplifier. Okay. All right. Now let's see why so saturation is a complicated phenomena. Let's try and understand. So we know that current keeps on increasing. Current keeps on increasing, but it doesn't increase as rapidly because R channel is also increasing. As I increase my drain to source voltage, R channel is also increasing, and eventually we are saying that the current saturates. Okay. Now let's see what happens here. So now you can imagine, as I've been saying, that as you make your drain voltage larger here, the inversion charge is the least here, and the inversion charge increases. And charge at any point in the channel is given by Cox. VGS minus VTHN is the effective gate voltage that creates inversion charge, and Vx is the voltage in the channel. So now again, let's consider this situation here. This is 2. Threshold voltage is 1. So 2 minus 1, I have 1 here. And the Vx here, as I said, keeps on varying. Now if I apply 1 volt drain to source voltage here, Vx that you see here will be 1 volt here and will gradually decrease to 0 here. So when I have 1 volt here, if I put 1 here, so I get 2 minus 1, I get 0. Which means that the inversion charge has become practically 0 here. And we call this case as pinch off. That I have sort of pinched off my channel here. The channel has been sort of removed here from this particular place. Okay. So note that as you keep on applying higher and higher voltage, you will reach a stage where the channel charge becomes 0 here. Okay. And we call this a situation as pinch off. Now obviously, if this region becomes a pinch off region here, channel charge becomes very small, you can imagine that this region here close to the drain will become a high resistance region. The resistance of this particular part becomes large as compared to the rest of the channel here. Obviously, you can see here that this is a simplification. I cannot have a charge which is 0. If I have 0 charge, I have no current then. If I have no electrons at all in my system, then of course no current can flow. So obviously there is some charge. In fact, this particular model, when the charge tends to become close to 0, this particular model also breaks down. It's not accurate. But what it is trying to show you is that as you apply larger and larger drain voltage, the inversion charge becomes very small. And because it becomes very small, you get a very high resistance region here. Very high resistance region here. Now, as a result of this high resistance region here, my current saturates. My current no longer changes with voltage. Now that's, why does it saturate? Okay, so as I said, saturation is a more complicated phenomena. Think of it like this here. I have 1 volt, and say at 1 volt, I'm right here, at this, somewhere here. Okay, why does the current saturate here? Now, if I apply 1.5 volt, what will happen? I have 1 volt. This is the situation here. Now I apply 1.5 volt, which means over and above 1 volt, I apply 0.5 volt here. So you have an excess of 0.5 volt, right? Where will this 0.5 volt get dropped? Think of this whole thing as a channel here. Where will it get dropped? That 0.5 volt will get dropped because this is a high resistance region here. it gets dropped practically here, close to this particular region. Okay, and because of this high resistance region here, so the idea is as follows here. Earlier, if let's say when my channel is uniform, think of this channel as a series of resistors. My channel earlier was uniform, and if you apply if you increase the voltage by a certain amount, let's say 0.1 volt, what would happen is that 0.1 volt will drop equally across all the resistors, right? Will drop equally across all the resistors, and the current would increase by a certain amount. Now, the situation is not like this here, but the situation is R is continuously changing. If this is R, this will become 2R and 4R or whatever. It keeps on increasing, right? But it increases sharply and the resistance here becomes very large. Now, if you increase the voltage by a certain amount, 0.1, what will happen? The entire voltage will get dropped across this region here, and hardly anything will drop here. Okay? The excess voltage that you apply gets dropped here, and nothing really reaches at this end here. Which means if the voltage across this particular element is not changing, it means that the current that is taken from the source side also doesn't increase. All the voltage that you apply after this particular point here, after pinch off, all the excess voltage that you apply here gets dropped close to this one here. Doesn't do anything to the channel here. Okay, the voltages and the electric field and everything else remains constant. And therefore, the amount of electrons that enter the channel, they remain the same. And there's a high resistance region here. All that it does is that high resistance region, it only collects whatever reaches from this side here. It only collects here. So this picture is simplistic. Don't think of, this region is actually not really like a resistor. It's more complicated than that. But all that I'm trying to tell you is that as you go beyond pinch off, any excess voltage that you apply gets dropped very close to the drain. Very close to the drain here is like a high resistance region here, and the excess voltage doesn't reach this particular point here. And as it doesn't reach this particular point, the current doesn't get affected. The current, depends on the electrons which are injected into the channel. So all that injection of electrons into the channel and all that remains the same. Okay, so this sort of picture is not accurate, but sort of telling you is that when you apply delta VD, if there's a high resistance region here, the voltage, the fraction of voltage which appears over here is negligible. It's negligible here, and therefore the current no longer changes. The current no longer changes, and you start seeing a saturation. You start seeing a saturation at this particular point. The current is no longer changing. Okay, at that particular point. The whole thing has become so high resistance that nothing really changes here. Now, so the point is that once you pinch off, any change in drain voltage doesn't change the current at all. Because anything, as I just said, anything above 1 volt, once you create a pinch off, anything above 1 volt, all that it does is that voltage is absorbed here, doesn't do anything here. So the current doesn't change. And if the current doesn't change, note that what happens is, once you reach that situation, the current does not change with voltage here. The current does not respond to drain to source voltage here. But the current responds to gate voltage here. As I change the gate voltage, I will change the inversion charge here. Right? As I change the gate voltage, I will change all this inversion charge, and therefore I will change the current. So what happens is, the moment you enter into saturation, you get your drain current responds to gate source voltage here. So you get a strong transconductance, but your drain current doesn't respond to drain voltage here. So you get small output conductance. And therefore now this device will become capable of amplification, because transconductance is much larger than output conductance. So once you enter into saturation region, your transistor is ready to amplify, because it will respond to gate voltage, transconductance will be high, it will not respond to drain voltage here, output conductance will be low. Okay. So as I said, the voltage at which this pinch off occurs is what we call as the saturation point. After this, the current saturates here. Okay. And therefore, we can see here at what voltage will it saturate? We can see that it's the point where inversion charge goes to 0, and inversion charge is nothing but Cox VGS minus VTHN minus the channel voltage. The channel voltage at this point is the drain to source voltage here, so it's VD, and at that voltage we are saying inversion charge goes to 0 here, so we equate it to 0, and we get VD sat equal to VGS minus VTH. So that's the voltage to create pinch off. Once the pinch off occurs, saturation occurs, and the current no longer responds to drain to source voltage here. First order approximation. But something interesting happens here. You apply voltage now, as I said, at 1 volt saturation has occurred, pinch off has occurred. Suppose you apply 1.5. If you apply 1.5, see if this figure makes sense now. If you apply 1.5, the voltage here will be 1.5. And as you go into the semiconductor, it will become 1.2, 1, or 1.3, 1.2, and eventually reach 1. And note, the moment the channel voltage becomes 1, what do I get? Inversion charge is 0. At the channel voltage, whenever Vx becomes 1, inversion charge becomes 0 here. So what has happened is, earlier, the pinch off was occurring here. Now the pinch off point has moved here. The pinch off point is moved left in deeper into the channel here. So this whole thing here that you see here has been pinched off. This entire region, the pinch off point starts here, moves here, and this whole region is sort of pinched off. It's a large high resistance region here. Okay. But note, has anything changed close to the source? No. Close to the source or drain and all that, nothing has really changed. Okay. So in effect, if you compare this situation versus this situation, what is the difference between the two? Look at the inversion charge and profile here. This situation versus this situation. What is the difference? Here, you know, as you go from here to the pinch off point, what is the total separation? The channel length. And now, as you go from here to the pinch off point, what is the separation? So, if this is what you call as the channel length, then now I have this region is called L dash. Right? Effective channel length. Effective region over which I have inversion charge here. That's L dash. Okay? Now, so the only difference between, as I go back here, between this is that the inversion charge starts from source and becomes 0 at a distance equal to L. Now, inversion charge starts from here and becomes 0, not at L here, but at L dash. So what is happening is, this is where you can see here is my channel. Inversion charge exists here. And after that is all pinched off region, very high resistance region. Okay. So this is where my channel has been removed. So my effective channel length is what we call as is L dash. And L dash gradually becomes smaller and smaller. As I apply even higher voltage here, my pinch off point will further move into the semiconductor. And my L dash will become a little bit smaller again. Okay. So, you know, there's a little bit of a issue here. You're thinking that this is a high resistance region here, but this is not the one which controls the current. Although it's a high resistance region here. So the picture, if you build a picture in your mind totally in terms of resistance, then you will think, well, this is the point that should control current. The highest resistance will control the current. It doesn't control the current. The current actually, so I'll show you a picture here, which will tell you what happens. Okay. So this is a simulation picture. Okay. It takes some time to digest. So this is my MOSFET, and what we have done is I've taken a cut line here. I've drawn a line very close to the surface as I go from left to right. Okay. As I go from left to right, I've drawn a line. And what the simulator gives me is, what is the electric field as I go from left to right to the other extreme. It tells me the electric field. Okay. So don't worry about these. These are N plus regions here, complicated. So now somewhere here is where my channel starts. Okay. Somewhere here is my channel starts here. And then as I reach the drain end, it's plotting electric field. So you start from here, channel starts, and as you reach the other end, drain end. So what happens is your channel starts here, and as you reach the drain end, look at what is happening to the electric field. The electric field is really becoming very, very large, very close to the drain. And now as you enter into the drain, you get a lot of electrons, N plus region. Remember, drain is an N plus region here, so the electric field collapses here. Electric field goes back almost to a very small value. So the picture that you should have in mind is that there's a very high field region, very, very high field region. And what happens is, in this high field region, whatever electrons, are injected from the source, they reach this particular point here, The moment they reach this particular point, what happens is they are swept by the very high electric field into the drain. Whatever electrons reach, the high electric field just pulls all those electrons and into the drain, and they get collected. So although it's a high field region here, this is not the one which controls current. Whatever number of electrons reach this high field region here, they immediately get collected. Okay, they get collected here. So the current is controlled by this part here. Whatever electrons are able to travel through the channel and reach this particular point here. Okay, is controlled by length. It's like you are going off the cliff, right? It's like water coming, and then this is like a cliff here. It's like a cliff here, and there's a waterfall, maybe you can think of, right? So the water is falling here. So what is the rate at which the water will fall? It's not going to be controlled by what height it is falling to. Okay, by the height through which the water is falling, it will control by the rate at which it is arriving at that particular point. Okay, and then it gets collected here. So you should think of this particular region as a region which will collect. Anything which reaches that particular point will get collected. It's a high field region here. But what controls the current is what arrives at this particular point. Okay, so that's the picture that you should build. So although I'm saying that this is a high resistance region here, what I really mean is it's a high field region. High field region which will collect all the carriers that reach at that particular point. Okay, so the idea then is that so this is a high field region here, don't worry about it. What controls current is this particular part here. This part is the one which, carriers electrons start from here, flow and reach this particular point. The moment they reach, they get collected. They go immediately to the drain. So now, if I compare my MOSFET here, this particular point, this is a MOSFET with an effective channel length which is equal to L. And this is a MOSFET with an effective channel length now L dash. So what we are saying is that as you apply higher and higher voltage here, the effective channel length becomes smaller and smaller. This particular point will move. Eventually, where will it move? It will move here. And this point remains fixed. So it will move here and eventually here and here and here. So effectively, your channel is becoming smaller and smaller. And if the channel becomes smaller, what happens to current? The length of the channel becomes smaller, which means its resistance becomes less. The resistance is from here to here, right? As I said, beyond this particular point, there's no problem in electrons getting collected. So what happens is the effective channel length becomes smaller and smaller. The resistance of the channel becomes a little less, and the current begins to go up. But not by a lot, because, this is like an exaggeration. This high field point, it moves actually very little here. It moves deeper and deeper, but because it's very high field here, almost the entire voltage gets dropped in a very, very narrow region. Okay, so the picture that we have then is the following. That what happens is, this is the point where pinch off occurs. But beyond this point, once pinch off occurs, the current doesn't become constant. It starts to increase slowly. Very slowly it starts to increase. Why? Because my effective channel length becomes smaller and smaller and smaller. Okay, so the current actually goes as whatever is the current at this point, ID sat, and it increases a little bit, 1 plus lambda times VDS here. So it starts to increase beyond that particular point. In fact, it should be VDS minus VD sat here. The excess voltage here is what controls the current here. So there's a parameter called channel length modulation parameter, which says that the channel length is reducing with voltage here and the current is increasing as a result of that. So this is the parameter lambda which models that particular phenomena, takes into account by saying that the current actually increases a little bit here. Is the counterpart of what we were talking about early voltage. Early voltage in bipolar transistor was as you apply larger and larger collector emitter voltage. Remember we had e to the power QVB by KT 1 plus VCE by VA. And a counterpart of VA is 1 by lambda. Lambda has units of 1 over voltage. And so this is the counterpart of early effect in MOS here. All right, so this is the picture that we have already. And so then the current starts to increase as you apply drain to source voltage. But what happens is channel resistance also increases as you apply drain to source voltage. So the current starts bending. And eventually you reach a point where you pinch off the channel, and once you pinch off the channel, then any excess voltage beyond this, any excess voltage is all dropped very close to the drain and doesn't affect the rest of the channel. First order approximation doesn't affect the rest of the channel, and that's why the current becomes constant. The next order of approximation is the channel length effectively becomes smaller and smaller, and therefore the current increases a little bit here. Okay, so that's the picture that we have as you go from all this is the linear or saturation region here, and beyond this particular point you have the linear or triode region, and beyond this particular point we have the saturation region. So that's the basic operation of the MOSFET. Okay. So one of the key parameters then is threshold voltage. Threshold voltage tells me that I need to apply that much voltage to create a reasonably strong channel in my device and allow current to flow here. And threshold voltage, from a circuit designer's perspective, threshold voltage depends on the following parameters. Threshold voltage has two parts. One part is a constant part that is decided by the way the MOSFET has been fabricated. So once you choose a particular technology, this is fixed for you. So VTHN 0 is fixed, gamma is also fixed, 2 phi f is also fixed. These are all parameters which are fixed. Okay, I'll give you the values in a minute. So what it says is that the threshold voltage, from a circuit designer's perspective, threshold voltage depends on the source to body voltage. How much voltage is there between source and body? And you can see here, as the source to body voltage increases, the threshold voltage also increases. Okay, and all others are parameters which are fixed here. Okay, so this is called surface potential. Examples are VTHN 0 is, let's say, 1 volt. Gamma, body parameter, is 0.7, and 2 phi f is 0.7. So as I said, from an analog design perspective, what you have to be aware of is my threshold voltage depends on source to body voltage. And once I know how much is source and body voltage here, I can find out what is the threshold voltage, because all these parameters are given to you. VTHN 0, gamma, 2 phi f, these are all constants provided, and you can figure out how much is the threshold voltage given this particular expression. Okay. Now, obviously, most of the time, what we want is threshold voltage to be low, and therefore we often try to make source to body voltage 0. Source to body voltage, we would like to keep it 0, but many times it's not possible, and therefore one should remember that threshold voltage varies with this parameter. As an example, you can see here this particular circuit. You can see two N-channel MOSFETs. Two N-channel MOSFETs are there. M1 here, M2 here. This is the source here, which is grounded. Gate and source are connected together. Gate and drain are connected together. Gate and drain are connected together. And let's say you have 3 volts at this point. Now, how do you calculate the voltages and all that? We'll see later on. But if you do the calculation, this voltage comes out to be 1.3. Okay, so 3 volt here. Something drops across the transistor M2, about 1.7 volt. And something drops across transistor M1, which is 1.3. Both transistors are identical. Both are identical. Why did the same voltage not drop? And note the current which starts from here, current obviously will not flow into the gate. Gate is an insulator. So the same current flows through M2 as well as M1. Same current flows. The transistors are identical, but I have different drops here. The drop here is 1.7 and the drop here is 1.3. Why? What is the reason? The reason is the threshold voltage. Note, what does threshold voltage really control? Threshold voltage controls the amount of charge in the channel. And therefore, it controls the resistance of the channel here. Now, in this case, if you note here, what is the source to body voltage? 0. Source to body voltage is 0. So, how much threshold voltage do I have? Basically 1 volt. You just substitute here 1 volt. While in this case, body is ground and source is at 1.3. So, I have source to body voltage which is positive, and if I plug it here, I'll get a higher threshold voltage here. So, this is threshold voltage is 1 volt and the threshold voltage is 1.4. So, this has a higher threshold voltage, and therefore, it has a larger resistance, and therefore I require a higher voltage, a higher drop as compared to this one. Okay. Now you may be wondering, why can't I put source and body? Why can't I short it? Can I short it? Source and body. Can I take the source and connect it to the body or not? Can I take the source here? What is preventing me? Why did I connect to ground? Take the source here. Body terminal is available, and just connect it here. What will happen? Okay, let's see what will happen. Let's go back to one of those figures. Okay, so note, these are two MOSFETs here. Think about M1 and M2. The source of this one is at 1.3. And if I connect 1.3 to the body here, right, source and body together, then the body goes at 1.3. So the body goes at 1.3, and the body has to be at the same potential, which means I'll have to make this also 1.3. And if this is 1.3 p-type and source was connected where? Ground. So if this body is at 1.3 and source is at 0, what has happened to your PN junction? You're forward biased. So you can't do that. All the bodies are, as I said, all the bodies share the same terminal. And that terminal has to be kept at the most negative point in the circuit. Okay, so we have to do that in my N-channel MOSFET here. I have to do this situation here. I have to keep all the bodies to the ground here. And when I do that, then the transistor, and if you stack transistors, you can see here, source to body voltage becomes positive, and therefore the transistor gets higher voltage, higher threshold voltage. So if you stack transistors like M1 and M2 and you had M3, M3 would have the highest threshold voltage, then M2, and then M1. Okay, so this is something that you need to keep in mind here. So so we are coming now towards the model. So eventually, if I have to make an amplifier and I want to understand circuits and design circuits, I need a model for a MOSFET. And model for a MOSFET, you can see here, would depend on where my MOSFET is operating. My MOSFET can operate above threshold, or it can operate below threshold, depending on what gate to source voltage I apply. Okay, so threshold voltage is a key parameter, which will tell me whether I'm above threshold or below threshold. Above threshold means strong channel. Below threshold means weak channel. I have electrons, but the electrons are very small. So that's the first distinction. The second one is, okay, I'm above threshold. I can be in saturation region if my drain to source voltage is larger than VD-SAT, or I can be in linear or triode region if my drain to source voltage is less than VD-SAT. So the distinction of where the MOSFET is operating depends on VTN and then depends on VD-SAT. These are the two voltages which decide VGS greater than VTN or VGS less than VTN, and VDS greater than VD-SAT or VDS less than VD-SAT decides where the MOSFET is operating. Note that if VGS is less than VTN, as I said, channel is weak, but if, let's say, threshold voltage is 1 volt, and you apply a gate to source voltage which is 0.5 or 0.1, is well below the threshold voltage, and in fact, this is the state we will call as cutoff. If the gate to source voltage is well below threshold voltage, your transistor is essentially in a cutoff state. It has very few electrons in the channel, and it will not conduct much current. But if you're close to threshold voltage, then of course, some current will flow, and we'll see how the current flows in the system here. So what we have is, for our analog circuits course, the most important region is this one, saturation region. This is where, for all the amplifiers, I will bias my MOSFET in this particular region, and then my MOSFET becomes capable of amplification here. So we need a model for the MOSFET in saturation region. We need a small signal model for the MOSFET. MOSFET has capacitances, so we have to understand all of that and put it together to build a small signal model for MOSFET here. Okay, so that's that will be the topic for next 2 lectures.